Hi everybody, my name is Lieutenant Dante Mazzotta. I'm from Villeneuve Cadet Flying Site, and I'll be going over your ground school lessons for this evening. Like I mentioned, we've got 4 lessons, and we're going to start by finishing off meteorology. So we're going to talk about GFAs, upper winds, and CFPS charts. At any at any point, if you have any questions, just let me know. Feel free to put it in the chat. But if you can hold on to the end of each individual lesson, I can go over your questions then and spend some time looking into your questions if I might not know the answers while I send you guys on a brief little break. So a little bit about myself, like I said, I'm a Gladiator instructor check pilot at Villeneuve Cadet Flying Site. I'm also the training officer there. I was a cadet at 523 St. Albert Royal Canadian Air Cadet Squadron in St. Albert, Alberta for several years. I've been teaching at the GPTC for the last 3 summers. I've had 9 students total, and I have around 150 hours total time in the Schweitzer 233A. So for for this lesson, we're going to go over the following teaching points. We're going to talk about graphical area forecasts, the issue time and validity periods, how to interpret GFAs, upper level winds, significant meteorology advisories, services available to pilots, and as well as satellite imagery. So starting things off, we're going to talk about a graphic area forecast overview, or a GFA. So if this is familiar to some of you, you'll already know what I'm going to be talking about. But if this is new to some of you, GFAs take time and practice to understand. We're going to go over the basics of them today, but you're going to get a lot of time to practice reading them and interpreting them when you're on course and onward. So the GFA is a graphic forecast for a specific area. So it's a series of charts that show the most predictable meteorological conditions expected to occur for a given period in a specific area. So again, big thing with this is that it's a forecast. It's not exactly what's going to happen. It's a very highly probable prediction of what you could expect. And it's very similar to if you watch the news in the morning, or if your parents have it on before you're going to school, and they see the big weather chart with the high pressure systems and the fronts moving in. They're very similar to that, except they don't move like we see it on TV. Some key things to note about GFAs: they are from surface level to 24,000 feet ASL, and they're designed mainly to meet general aviation and regional requirements for pre-flight planning. So big thing with that is, as a pilot, it's not only important to know how to read a GFA, but to interpret what they're saying and how that's going to affect your flight and your operation. So when you go on GPTC this summer, you're going to have a weather briefing every morning, and they should be going over the GFAs and what you could expect for the forecast in your area. Same thing at the CFS, the cadet flying sites. When you have your license, you'll be doing weather briefings in the morning. And on the PPTC as well, you're going to be checking out the weather before you go across countries, before you go for your flights during that day. And you'll eventually start to determine what's good flying weather and what's not good flying weather. GFAs are automatically amended by AirMet bulletins whenever significant weather changes. And there are 7 distinct GFAs across Canada Canada is responsible for providing of air traffic control services in these regions as well. So I'll show you how we get there in a little bit, but you can see that there's a Pacific region, a Prairie region, Ontario and Quebec, the Atlantic region, which is mostly the Maritimes, and I believe part of Quebec as well, Yukon, Northwest Territories region, Nunavut, and the Arctic region. So if you were if you attended some meteorology classes last week, you would have talked about METARs and TAFs. So just like METARs and TAFs, GFAs also have issuing times and validity periods. They are issued 4 times a day, also approximately half an hour before the beginning of a forecasted period. So you'll see that the issuing times are at 23:30 Zulu, 05:30 Zulu, 11:30 Zulu, and 17:30 Zulu. Again, you'll have to convert that to your local time. So in Northwest region right now, we're -7 Zulu because of the daylight savings. So your 17:30 Zulu would be 10:30 a.m. And then they are issued every 6 hours at 0 Zulu, at 0600 Zulu, at 12 Zulu, and 18 Zulu, respectively, as you can see on the chart there. The GFAs consist of 6 charts in total. They've got three cloud and weather GFAs, which is a short-term and mid-term and a long-term forecast, and as well as a three icing and turbulence forecast. Same thing for a near-term, mid-term, and long-term forecast for freezing and turbulence. So if you want to go ahead and draw down that table, those ones are pretty important there. The thing with like the long-term forecast is you can see how the conditions are going to change throughout the day, right? Again, they're forecasts. So for example, let's say you're reading the GFA for your current time, which let's say is 12 Zulu, and you look at your next issued GFA, which is for 18 Zulu. So let's say at 12 Zulu, you see that there's rain to the north of you, which is at your current time. Okay, there's rain to the north of us. And then you look at the 18 Zulu GFA and you see that the rain has passed to the south of you. Then you could expect that there could be some rain within that 6 hour period, for an example of how the forecasting works. So how to interpret the GFA. So this is where it's going to get a little messy. And if at any point you have any questions, let me know. If you want more practice at the end of the class, we can definitely do that. But again, this is just the basics. We don't expect you to be able to recite a GFA entirely right now. So this is a picture of an older version of a GFA. The newer ones still look relatively the same. But you'll be able to see that there's different sections. So if I get my laser pointer out here, at the top here, we've got the title box, and the title box is important for having the region and the validity periods of the forecast as well. That's where you would look. Next, you would have underneath it the legend box, which has different symbols that you might see on the GFA, as well as a nautical mile scale bar that's included there as well. And then beneath that is the comment box. And in this one, you'll see different weather information that's still relevant, but is almost too big to fit on the GFA itself. And we'll go over what that looks like in a couple of slides, and I'll actually take you to the CFPS website where you can look for them there as well. Other important things to note, the wind's speeds are expressed in knots, KT. I shouldn't just say the winds themselves. The speed that the fronts and pressure systems move as well will also be indicated on there. The height for clouds is going to be in hundreds of feet above sea level unless otherwise noted. So if there's no UGL next to a height, you can assume it's above sea level. And then the times are going to be stated in UTC or Zulu time. Okay. So GFAs are spatial coverage qualifiers. So some things you could see for convective weather. So like showers or thunderstorms, things like that. The abbreviations are in the chart there and their description. So isolated means that the spatial coverage is less than 25% of that area. Scattered is about 25 to 50%, and then numerous would be greater than 50% of that area. If this doesn't make sense to you right now, when I show you a GFA, you'll probably see some isolated or scattered, or what I'll show you in the next slide, you'll probably see it on there, and that'll hopefully give you a better understanding of what I am telling you here. So non-convective weather. So non-convective precipitation ceilings, and low stratus, icing, and turbulence will also use these abbreviations. So local LCL is less than 25%, patchy is 25 to 50%, and extensive is greater than 50. So again, when we actually look at a GFA, this is where you'll see these different abbreviations, and hopefully it's going to make a little more sense for you. And again, sorry, I just want to say if I'm going too fast at any point, please let me know and I can slow down. So some synoptic features of the GFA. So the speed of the synoptic feature, so fronts, is indicated by an arrow and a speed value when it's greater than 5 knots. So if you look here, where that H is, there's an arrow. I think it says new, and then there's a speed there as well. That's going to indicate the speed is moving. Yes, I can slow down. Sorry about that. If you need me to go back to, just let me know. Quasi-stationaries are used for when the fronts are moving at a speed of less than 5 knots. It's not pictured on this slide, but it is in a couple slides. Sure. I'll finish this slide and then I'll go back a slide. So as you can see in this picture of the GFA here, you see a high pressure system that's moving eastward at 15 knots with the associated cold front moving southeast at 10 knots behind it. Okay, so I'll give you guys a couple seconds on this slide here, and then I'll go back to the previous slide. Okay, so there's those non-convective weathers. If you need the convective weather as well, just let me know. And then if you guys could just give me a thumbs up when you're good, I'll keep moving on. Okay. Okay, moving on. And I'll give you guys a couple seconds on this slide as well. So for the synoptic features, like I said, you'll either see an H for a high pressure system or an L for a low pressure system. They'll include the speed and an arrow with the direction that it's moving. And as you look at the different GFAs throughout the day, you'll see the front move and where it is every 6 to 12 hours. And same thing with the pressure systems and precipitation. Okay, isobars on the GFAs are included, and they're displayed for every 4 millibars as they increase or decrease. As you can see on the line, or sorry, the GFA here, they're the black squiggly lines throughout the GFA. And you can also see on this GFA, there's a lot going on. So don't be too worried if you don't understand everything that's going on. Like I said at the start, knowing what a GFA means and what it's saying and what the symbols are will come with time. With time and practice. So some things to keep in mind when we talk about visibility. Visibility is the forecasted visibility that is measured in statute miles. P6SM, which actually stands for prevailing visibility, is greater than 6 statute miles, is used when the visibility, like I said, is greater than greater than 6 statute miles. So it's not plus 6 SM, it's prevailing visibility greater than 6 statute miles. And what that means is the greatest distance that can be seen horizontally in at least half of the horizon. So sometimes weather reporting stations will use a visual reference point or like a landmark as a reference. Another example is when you have 2 to 4 statute miles light showering rain, which is what that 2 to 4 SM minus SHRA stands for. The visibility is expected to vary between 2 and 4 statute miles with light showering rain. So very similar to what you might see on a TAF. As you can see on this GFA in there. Okay, also on GFAs, they're going to talk about different weather and obstructions to the vision. And this is only going to be mentioned when the visibility in the forecast is going to be 6 statute miles or less. The standard abbreviations are used to describe weather and precip with or without obstruction, which is going to be the same as a METAR and TAF. Intermittent and showery precipitation is going to be a green dash board or a dash green border and shaded with lines to enclose the area of precipitation. Like you can see in the picture beside there what it would look like, and then we'll go look for it on a GFA shortly. And then for obstructions to vision, usually you will see it in orange. So that would be things like smoke, haze, fog, all of that type of obstruction, where it just makes the horizon a little bit harder to see. Continuous precipitation is going to have a solid green border with shades and shaded with dots, which is going to be that top green symbol on the picture there. And you can see on this GFA here as well, there's some precipitation in southern Ontario. That's what it would look like on the GFA. Now talking about clouds a little bit. So cloud bases and tops of the forecasts are going to be on there, and they only go from the surface to as high as 24,000 feet. So you won't see clouds reported higher than that. And just to be clear, it's also going to be an ASL unless indicated for AGL. Convective clouds are going to be abbreviated as CU, TCU, ACC, and CB. So cumulus, towering cumulus, altocumulus, castellanus, and cumulonimbus. And the tops of the convective clouds are indicated even if they extend above 24,000 feet. Cirrus clouds are not depicted on these charts. Okay. Organized charts, or sorry, organized clouds. So that means they have a scallop border enclosing an area of clouds where the sky condition is going to be either broken or overcast. So that's going to be like a solid layer of cloud. And that's what it would look like on the GFA. So you can see that they've got that scallop border going all around a certain area, which basically is indicating a ceiling. And then it's going to tell you the type of cloud. So you've got broken cumulus with the top of the cloud at 8,000 feet and the bottom of the cloud at 2,000 feet. Again, above sea level. Non-organized clouds and with a visibility of greater than 6 statute miles. A scallop border is not going to be used. They're just going to have the cloud type with the sky condition with the cloud height in tops and bases. So in this case, it would be scattered clouds, tops at 5,000 feet and bottoms at 3,000 feet. If you have multiple layers of clouds, they will have the bases and tops indicated as well. And the amount of cloud each layer is based on the amount at that cloud level and not the total amount. SKC is sky clear and SCT is scattered. I'll write that in the chat for you. Okay, obstruction to vision. So kind of like, what I was mentioning a couple slides ago. These are going to be areas of obstruction not associated with precipitation, where again the vis is less than 6 statute miles, and it's going to be enclosed with a dashed orange line. So again, that could be due to smoke, haze, fog even, and it's going to indicate roughly the visibility as well. So in the example, the diagram could show 1 to 2 statute miles in smoke. Surface-based layers are going to have the obscured abbreviation there to describe those surface-based layers. And the vertical visibility into the surface-based layers is measured in hundreds of feet above ground level. So on the example here, what it would look like on a GFA, if the vertical visibility is between 3 and 500 feet AGL, it would be indicated as local obscured ceilings 3 to 500 AGL. And again, that local indicates that it's less than 25% coverage of that area. And that's something very common, at least in Alberta in the fall, where you'll start seeing that for fog in the mornings. Oops. Okay, next we're going to talk about wind barbs. So these are for surface winds when the wind speed is greater than 20 knots. So I know in the example here of what the wind barbs look like, you see one for 5 knots, 10 knots, and 15 knots. Those ones individually will not show up, but they're good to know what 5 looks like or what 10 looks like, so that when you see the wind barbs at 20 and what the other arrows indicate, that's kind of how you know how much wind there's going to be. So each barb represents about 5 knots of wind, and they're going to be also rounded up to the nearest 5. If you see a triangle on the wind barb, that means it's 50 knots of wind, which is quite a lot. Although not very common, but I have seen them, so they do exist. They're not just placing that here just because. It does happen, especially in the prairies. Now, if there's a gust, the wind gusts are going to be indicated by the letter G and the peak gust speed in knots. So on the example at the bottom there, you can see the wind gust is 25 gusting 35 knots. And they also point in the magnetic direction that the wind is blowing. So in this case, the wind direction is blowing approximately 270 degrees true. Sorry, I correct myself, the true heading, not the magnetic heading. 270 degrees true at 25 knots, gusting 35 knots. So hopefully that makes sense. Give me a thumbs up if those wind barbs make sense. A couple. Okay. So any questions so far? That's the weather part of the GFAs. So I'm going to stop sharing my screen here, and I'm going to show you how to actually find the GFAs before we start talking about icing and turbulence. So okay, can everyone see my screen okay? Yeah, thumbs up if you do. Perfect. Okay, so when you want to look for a GFA, you're going to go to the internet and you're going to type in CFPS, which is going to bring you to the welcome page. When you were talking about METARs and TAPs last week, those can also be found in that weather and NOTAM section. But for the GFAs, they did fix it. It was a bit of a problem for a little while. They made a GFA specific page to make it more user friendly for all parties involved. So once you get to this GFA page, what you're going to do is you're going to find the region that pertains to you. So I'm going to use Prairie region for an example. And there's a lot going on here, as you can probably tell. So first I'm going to go off by going over the legend like I talked about at the start. So first on the top here, we've got the title box, right? So it tells you that it's for the Prairie region and that it's clouds and weather. You'll also note that it's also in English and French a little bit. Then you've got the issued period. So it's issued at 23:25 Zulu and it's valid at 1200 Zulu. So this is going to be valid for 6 p.m. Or sorry, 5 p.m. My apologies for the time change. Then we have the legend box. And the legend here shows symbols for different weather phenomena you might see. So this R-shaped symbol with a TS indicates thunderstorms. The ones at the bottom here are freezing rain, freezing drizzle, and then the triangle with the dot is pellets. Something else you can also note in this used to be in the title box, but it's now kind of affiliated with the comment section. Heights ASL unless noted, and cumulus, towering cumulus, and alto cumulus castellanus implies significant turbulence and icing, and CB implies low level wind shear. So that's just for some knowledge. That's kind of what you could assume if you see that on the GFA. In the comments section, so this is kind of what I'm saying, where it includes other weather notes. If you look on the GFA itself, you'll see there's something that shows the letter A, the letter B, and the letter C. I don't see where the letter C is, but oh, over the Rockies. So over northern Saskatchewan, you've got the letter A and the letter B, and you can see that there's more weather conditions associated with that front, that upper front that's passing through northern Saskatchewan. So when there's already a lot going on the GFA and they don't want to add a little bit more, they're going to add a little comment box with the letter A, B, C, D, things like that. And you'll find the comments in the comment section to what weather is going to be associated there. Does that make sense? Give me a thumbs up if that makes sense. Okay. Next up on the GFA. So you can see that there's a dark bold border that shows the prairie. So that's the region that this is relevant for. So first off, we'll start by looking at the black squiggly lines. Those are all the isobars. The closer the isobars are, the steeper the pressure gradient is going to be, so the windier that it's going to be. And you can see that as the further south you go, they increase by every 4 millibars, right? And the millibars are indicated, the numbers are on the right side of the GFA there. Over, I guess, Alberta, Saskatchewan, you can see that there's an upper cold front moving at a proc and an upper warm front moving mostly eastbound at 35 knots. You can also see over Slave Lake in Alberta, there's a wind barb there with a 25 gusting 40 knots of wind, roughly going 270-ish degrees to the west, and bunch of different cloud coverages. So if we look over the Edmonton area in Alberta, you can see that there's going to be a scattered layer of cloud, tops at 24,000 feet, bottoms at 18,000 feet, and a few layer of cloud tops at 10,000 feet, bottoms at 8,000 feet, and that P6SM prevailing visibility is greater than 6 statute miles. So this is for 5 p.m. Now, if we wanted to go look at what the 11 o'clock GFA is going to be, we would hit the next button, and then it's going to take us to the next validity period, which is issued at the same time, but it's going to be valid at 11 p.m. tonight. So you can see that the front has moved to the east. There's some more precipitation over northern Manitoba, but still quite a bit of strong wind over central Alberta, and especially over the Rockies. The high pressure system in southern BC is still there, and lots of stuff going on over Manitoba. So that's how you read the weather and cloud and weather GFAs. I know that's a lot, but does that make sense? If you guys want more practice, we can definitely go over it at the end of the class, but I definitely need to keep going with the other content we've got for GFAs here. Yeah, so somewhat makes sense. Again, if this is new to you, it's not going to make any sense. These take a lot of time and a lot of practice to really not only just read what it's saying, but interpret what's next. Okay, so now continuing on with interpreting GFAs, now we're going to talk about the icing and turbulence and freezing level charts on a GFA. You guys can still see my screen okay? Just give me a thumbs up real quick. Perfect. Okay, so the icing, turbulence, and freezing level GFA shows forecasted areas of icing and turbulence, as well as expected freezing level for a specific time. So it's very similar to a cloud and weather one, except for different things. It's going to show the type of turbulence, including the severity of it and the base and the tops of icing as well. So this is what the freezing levels look like. They're very similar to contour lines, and they indicate the icing turbulence and freezing charts by the dashed line. The height is measured above sea level, and it's going up in increments of 2,500 feet. So you can see in this example here, starting one at surface level, then at 2,500 feet, and then at 5,000 feet again for that freezing level. I'm not sure what exactly from the GFAs are going to be on the final exam, but when we go over some confirmation questions, I can kind of make them sound like what you could see on the exam. I don't know what's expected currently. So when we talk about icing, icing is going to be indicated by blue coloring on the GFA, as you can see in that top picture there. It's going to show the base and the tops of each icing layer measured in feet above sea level again, and it's going to also include the um, type of icing as well. So it's going to be mixed, rime, or clear. So and you can see in this example here, we've got mixed icing. And as well, when I show you the GFA chart for icing and turbulence, I'll show you on the legend box. It's going to show you the intensity and what these symbols mean. So, oops, I'll give you guys a couple seconds there. So that's what icing would look like on a GFA. Not super common in the summer, but definitely in the late fall, winter, and early spring, you definitely see a lot more icing present in the atmosphere. Next is going to be on turbulence. So turbulence shows whenever there's moderate or severe turbulence. It could be in the forecast. Just like icing, the tops and bases of that turbulence is going to be indicated in feet above sea level. And if there's mechanical turbulence, low-level wind shear and significant low-level jets will also be indicated on there as well. Yes, I can slow down, sorry. So for example, on here, this is where you can see the different abbreviations and the type of turbulence. So for this example here, you've got clear air turbulence, or CAT, with the bases at 8,000 feet and the tops at 20,000 feet. Okay, and now we'll go back to the icing and GFA. So how to find this? Again, same thing. Once you go on the GFA page on CFPS, you'll notice at the top here, there's going to be previous, next, and switch to icing and turbulence. So you would click on that. And oh, that's the one that I want there. So now you can see there's also a whole lot of stuff going on here. So the title box works the same. The legend box, the big difference here is that this shows you the intensity of the icing and the turbulence. So yeah, you can see moderate icing and severe icing, and then mod turbulence, severe turbulence. Um, and then, yeah, a lot of stuff going on again with those fronts that are associated and moving on through the prairie. So you can see that in the blue, there's your icing. The red, there's your turbulence. These thick black arrows are the low-level jet streams. So you can see in northern Alberta, it says L level jet 50 knot. So that means there's your low-level jet moving 50 knots in that direction that the arrows are pointing. Also, beside that, you can see that you've got more clear air turbulence, moderate clear air turbulence, tops at 28, bottoms at 20,000 feet. And then the dashed lines all throughout kind of Alberta mostly and some of Saskatchewan. Those are your freezing levels there, and that's where you see that 050, the freezing levels at 5,000 feet. ASL. Over southern Alberta, you can see there's another moderate type of turbulence from surface, which is SFC to 14,000 feet. And the MTW is mountain wave with a bit of mechanical turbulence there as well. So that's just all the air coming off of the Rockies. So hopefully that makes a little more sense. The comment box still works in the same fashion that if there's a lot already going on in a certain area, they'll just put a letter there and then it's going to go into the comment section. The difference between AGL and ASL. So ASL stands for above sea level and AGL stands for above ground level. So, for example, in northern Alberta, where we're saying 5,000 ASL, so 5,000 above sea level, you'd have to see what the actual elevation above the ground is, or sorry, above sea level that, let's say, Fort McMurray is. So if Fort McMurray is 2,500 feet above sea level, well, the freezing level is actually going to be 2,500 feet above the ground level or 5,000 ASL. So you kind of have to do a little bit of mental math to convert that. But that comes, again, that's not going to be expected for the exam. That's just more knowledge for when you go on course. Yes, not next week, but the week after, there's going to be a review for all the classes that have been taught. I'm not sure exactly what the schedule for it looks like yet, but I know that the instructors are currently working on review for the final exam. So this week is week 9. Next week is week 10. Week 10 has the last new content that's going to be taught. The week after that, so the final week of January, is going to be entirely for review. So no new material, just review from everything that's been taught. Okay. Um, okay, next we've got upper level winds, temperature, and forecast, so FDs. So this is going to be the forecast of wind and temperature at altitude. Usually they're issued twice a day at 000 Zulu and 1200 Zulu, and they're generated automatically. And they're issued for approximately 140 sites across Canada. And keeping that in mind, sorry, it may not be issued for your exact airport. So for example, I fly at Villeneuve Cadet Flying Site, which is about 45 minutes driving northwest from the Edmonton International Airport. Villeneuve doesn't have a reporting station itself for the upper level winds, but Edmonton does, right? So we would have to use Edmonton and kind of expect that it's going to be the same for Villeneuve. Or another example in Mountain View, Ontario, it's kind of in between Ottawa and Toronto. So Mountain View / Trenton doesn't have a weather reporting station for the upper winds. So we kind of have to use Toronto and Ottawa and kind of find the average between the two of them and maybe expect that the winds could favor one or the other, or it might be a little different. So for low level winds, they're going to be for 3,000 feet above sea level, 6,000 feet, 9,000 feet, 1,200 feet, or sorry, 12,000 feet, and 18,000 feet. And they follow the format of DDFFTT. So the first two digits are going to be for the wind direction in degrees true to the nearest tenth. The two Fs are going to be for the wind speed, and then the T for temperature in Celsius. One thing that's important to note is that winds at 3,000 feet have no indicated temperatures, as the temperature is going to be similar to the surface. So we'll keep that in mind. I believe the next slide here has an example of what the upper winds look like. And then once I go over the FDs, I'll show you where to find them on CFPS. And then I'll give you guys a quick little break here. So here's what it looks like. At the top, you'll see the station that it's for. So this is out of, I'm not even going to try pronouncing that, somewhere in Quebec. It's going to give you the for use time, so where it's valid for, but they also have validity period valid from when the forecasts are made. So those are also really important to look at because it's like the GFAs and the METARs and TAPs, they have an issued period and a validity period as well. And then 3,000, 6,000, 9,000, 12,000, 18,000. These ones are going to be more pertinent for the GPTC and the PPTC because you fly at altitudes so close to here. Again, these are above sea level. So um, TT is for the temperature. So if we look at this first line here, so for use between 17 Zulu and 21 Zulu, at 3,000 feet, again, remember there's no temperature indicated. So it's going to be 040 degrees true at 12 knots. At 6,000 feet, there's 030 at 16 knots. And again, it has a temperature, so it's actually minus 12 for the wind. Sorry, for the temperature. And then you can see that for the next validity period, 21 to 06, same thing. You can see that a difference here is that the wind picks up. So an example of how I was mentioning of knowing what the winds are going to do and how they are going to affect your flying for the day. If you were flying in this validity period, I'm not sure what the time difference from this part of Quebec would be in UTC. I'm going to say maybe about -4 or -5. So you could be flying. You'll see that the winds shift dramatically from the north and they increase by quite a bit too. So those are some things when you're doing your weather briefing that you want to look for in the patterns. For 3,000 foot level winds, the wind is actually going to be omitted when the ground level is greater than 1,500 feet. So for example, at Villeneuve Airport, we are 2,250 feet above sea level. So when we look at the upper wind reading for Edmonton, we have no winds for 3,000 feet because that's only about 800 feet above us. So it's going to be pretty similar to what the surface winds could be. Is usually the expectation there. But again, we still look at what the upper winds at 6,000 feet would be and also plan for those. Temperatures are not forecasted for the 3,000 foot level, like I had mentioned. The code 9900, just like Mattars and Taps, if the winds are light and variable and less than 5 knots, you might see those. And wind speeds. So this bottom point here is actually for the wind speeds above 24,000 feet. If the wind speed is over 100 knots, they're going to be coded by adding a 50 to the wind direction and subtracting 100 from the speed. That will not be tested, so don't worry about that. That's more so for like IFR stuff. And just for an example, that's what those upper level winds look like for above 24,000 feet. So unless you're flying high performance aircraft, I wouldn't worry about this just yet. Okay, I'm going to talk about significant meteorological advisories, or SIGMETs for short. So these are short-term weather warning to aircraft in flight, and they indicate severe weather and hazardous weather conditions that either have occurred or could expect to occur. So things like thunderstorms produce severe turbulence and some severe icing, squall lines, mountain waves, and volcanic ash as well. So these are some of the SIGMETs that you could see. And sometimes if your aircraft have them, SIGMETs that amend GFAs can be broadcasted on certain navigational aid voice channels. Again, oh, sorry, went too fast there. So again, like I said, short-term weather warning systems for the aircraft in flight, they automatically amend the GFAs and they're updated at least 1 hour before the stated end of that SIGMET and updated as needed. So some headers to include the types of phenomena would be WS for normal, WV for volcanic ash, and WC for tropical cyclone. Okay, services available to pilots. So as a pilot, we have the luxury of phoning people and looking up different information places to get the weather information that we need. So aviation weather briefing services is a number that you can call to get weather briefings to you and pertinent NOTAMs from the flight information centers in your region. The phone number is on the slide here, 1-866 WIX brief, or weather brief for short. And you can call these guys and they'll basically give you, as best as they can, a good weather briefing of what's expected for your route. This is also very good for pre-flight planning and in-flight stages as well. And they are services that are specific to an aerodrome or an airport advisory and local weather observations. So they kind of do what their best through locally provided weather stations. Sorry. So you won't call these guys on the GPTC, but you probably will on PPTC when you're doing a weather brief for cross countries. Okay, so there's a bit in this one here. Transcribed weather broadcasts, or TWBs, are mean of mass decimation of aviation weather information, broadcasted on NDBs primarily, and they're also accessible by phone. And the number there is going to be listed in the CFS, and this is all the information that they can broadcast to you. So flight precautions, some SIGMET, significant weather on route, the upper winds, NOTAMs, things like that. Okay, CFPS, so that's the Collaborative Flight Planning Services. That's the website that we were just on. Oops. Again, an excellent resource for weather information. It is relatively new. It has replaced the previous website, AWWS, which was way better in my opinion, but it has the same information and it's displayed in the same way pretty much. It's got satellite imagery, radar, forecast, charts like we saw. Another resource you have is the Pilot Automatic Telephone Weather Answering Service. The phone number is in the CFS for select locations, so you would just have to see where it's available, and they might have the forecast, icing conditions, and winds for you, and any other PIREPs or pilot reports that are passed on to them. Automatic Terminal Information System, so or ATIS, operates kind of like the PAT was, but it's a continuous reading of conditions given at a at a specified location. So most airports have an ATIS. It's accessible by its assigned VHF frequency, and it's going to have different phonetic identifiers as the weather and information and time changes throughout the day. So Villeneuve Airport, Edmonton, those guys, the bigger airports have ATISs. Smaller airports or the airports that don't operate 24 hours a day might also have an AWOS, which is an automatic weather observation system. Similar to an ATIS, except an ATIS is the information is provided to you by a human that reads through it. AWOS is an automated system that kind of just takes a snapshot of the sky. And similar to the other two is the LWIS, or the Local Weather Information System, is usually for smaller uncontrolled airports, but it just has no phonetic identifiers and it's usually less accurate. Almost done here. On CFPS, you have different weather imagery. So if you want to get some satellite or radar imagery, you can find that on CFPS if that's what you would like. Usually for us in the gliding program, we just look at the weather radar. Haven't really looked too much at satellite imagery, but it's there if you would like to use it. Okay, I know that was a lot. Um, let's interpret this GFA just a little bit, so I can give you guys a little bit of a break here. Okay, so if I could maybe think of an exam type question, an exam type question you might see is what type of precipitation could you see in that green area? So what type of precipitation do you see there? Is it intermittent? Is it continuous? You guys can go ahead and put it in the chat there. That might be an exam type question. Yeah, good. It is continuous and you can see from that solid green line going across. Another type of question that you could see is how fast is the low pressure system moving and in what direction? So how fast? Yeah, east at 10 knots. Very good. And again, indicated by the arrow and the uh, speed. And let's see what else I could see here. So yeah, those are some type of questions that you might find on an exam for weather and cloud. Now, if we look at icing and turbulence, um, okay, um, I guess kind of similar. What direction and how fast is the low-level jet moving over, I guess it's kind of northwestern Ontario. Yeah, so it's moving at 50 knots, and in what direction is it moving? Good. Another type of question that you could see is what type of icing do you see over Toronto? So at the bottom of that GFA there, what type of icing do you see over Toronto? Yeah, so it's mixed icing. Good. And what's its severity, or sorry, its intensity and the tops and bases for it? Yeah, so moderate icing, mixed icing, good. And the cloud, or sorry, the icing tops and bases, what would that be? Yeah, good. So not quite flight level 60 and 30. So flight levels only start for altitudes above 18,000 feet, just so you know. Um, so it's going to be mixed icing with moderate icing, I guess. Tops at 6,000, bottoms at 3,000 feet. Good. What does ADA stand for? Yeah, perfect. All right, and I'm not going to go over these. Okay, are there any questions regarding um, the what we've talked about so far? I know that was a lot. Hopefully, it kind of makes sense. If you guys want more practice at the end of the class, we can do that. But in the meantime, I'll give you a 10-minute break, and we're going to get started on our next lesson. Again, if you have any questions from the previous class, just try and save them till the end. I've got 3 other classes still to go through, but I'd be happy to stay on for a little while longer at the end if anyone still needs help with some GFA stuff. So with that in mind, we'll get started on 406.01 instruments. So the first type of, or sorry, the main teaching points we're going to go over for this class is going to be talking about the pitot and static systems and errors, describe airspeed indicator system and its errors, describe indicated and true airspeed, describe the altimeter system and its errors, and describe the VSI and describe the variometer. So first things first is we're going to talk about the pitot and the static source. Okay, so a brief overview of what we can see in this picture here. So we've got the pitot tube and the static port. On most aircraft, they are in separate locations on the Schweitzer 233A. They are two separate things, but they're attached at the same spot. The airspeed indicator is the only instrument that is attached that uses the pitot tube, while the static port is connected to all three of these basic instruments, the airspeed indicator, the altimeter, and the vertical speed indicator. So we'll start with the pitot tube, which I know it's kind of hard to see, but it's in that red circle at the top there. On the Schweitzer 233, the pitot tube is on the top and the static port is on the bottom. There's another picture coming up where you can see it a little bit more clear. But the pitot tube is connected to the airspeed indicator and it measures the dynamic pressure. So what it wants to do is it's positioned to get as much clean, free flowing air as it can. So it's going to be positioned clear of any slipstream and other turbulent spots on the aircraft. And it's going to face the line of flight. The pitot tube on our gliders is a very delicate piece of equipment that can bend or break easy. As you can see, the glider currently has its nose down in this picture, and sometimes it's very easy for the pitot tube to get bumped into and then you bend it, which if it's not centered correctly can misread your airspeed by anywhere from 2 to 5 miles an hour, which is pretty significant. So that's why we want to be as careful with that as we can. Sometimes the pitot system has a heating element to it. Our gliders do not, but 172s and aircraft like that do. And that's to break off any type of icing, which we might talk about here. So the pitot source can be blocked by moisture, ice, dirt, debris, a crack in the tubing, or even bent tubes. A complete blockage will cause the airspeed indicator to read like an altimeter, and a partial block can either be a partial block or leak in the system, or will cause the airspeed indicator to rotate back to zero. So the pitot tube is designed for the passage of airflow to enter to the airspeed to the instruments, and the reason why the airspeed indicator might read like an altimeter in a complete blockage is because the ASI is connected to the static port and it's getting that static pressure as well, and it's not getting the ram air or the dynamic air, so it's going to start reading in a similar fashion to an altimeter as the aneroid inside of it expands and contracts to the atmospheric pressure. ASI stands for airspeed indicator. A partial block, so the pitot tube is going to read similar to the static port, but it's also going to read the difference in pressure between the pitot and the static port. And so if they have pretty similar values, it's just going to read zero. Okay, the static tube or static port. So as you can see on the 233 here, this metal tubing, I guess. The top, like I had mentioned previously, is the pitot tube, and on the bottom is the static port. The static port or the static tube is vented to allow air pressure to equalize with the outside pressure. So it's measuring the ambient pressure, atmospheric pressure. The vents are located on opposite sides where they cannot be affected by pressure. And the airspeed indicator or the ASI, the vertical speed indicator or VSI, and the altimeter all use the static source. And I'll show you another photo here of what they look like on other aircraft, so you might be more familiar with it at a later time. Don't need that. So here's a pitot tube, pretty straightforward. They all kind of look like this in some way, shape, or form. On the 172, they're usually found just underneath the leading edge of the wing in the center of the airflow. And, oops, hang on here. Can't, for some reason, get to my other thing because there we go. Airspeed and the static port on a 172 on the tow planes that the air cadet gliding program uses, they look kind of like this. It's just a little circle with a hole in it, which is what allows it to vent. They can be hard to miss, and in this case here, you can see it's kind of blending in with the paint scheme of the airplane. So when you're doing your walk around on a powered aircraft, it's very important that you find where the static ports are and make sure that there's no blockages in those areas. Just pulling up the slide again. Yeah, you definitely need to look very closely because it can be easily missed. So essentially what's happening with the static port or the static tube is it's reading the difference in atmospheric pressure causing the mechanism inside of each instrument, which is an anorak capsule, which we'll talk about a little bit later on, to either expand or and contract. And that's how we get the readings on the instruments. So there are some blockages that can happen. So in a climb, the airspeed indicator, the vertical speed indicator, and the altimeter will underread and slowly catch up when the aircraft returns to level flight. So what's going to happen essentially is that it's lagging behind the correct reading on the instruments. And in a descent, the ASI and altimeter will overread. So it's gonna notice that there's a change in pressure. So it's just gonna descend in that sense. So it's gonna overread. It's basically just reading faster than what the aircraft is flying at. And the vertical speed indicator is going to indicate a less than true rate of descent. So again, we'll talk a little bit more about what each instrument does a little bit, but just a brief overview. The vertical speed indicator tells you whether or not you're going up or down. And a little bit more accurate than the altimeter, but we'll get to that in a minute here. So how to create an alternate static source. Well, a popular Transport Canada answer is just to break the glass on the vertical speed indicator, which I've heard of, but haven't actually had to do it myself or flown in an aircraft where that's happened. But you can also pull out the tube from behind the vertical speed indicator, especially on the gliders as you can reach them. But for a 172, they're a little bit harder to get at. Again, I'm sure it has happened, but in the time that I've been flying the last 10 years, hasn't happened to me, hasn't happened to anybody I know. So a mnemonic to help you remember what happens for static port blockages is suckpud. So static underreads and climb, pitot overreads and descent. Okay, so we're going to talk about the airspeed indicator now. So this is what it looks like inside of the 233. You can see that right now it's on the ground, so it's reading 0. And there's different colors and speed ranges that you can see. There's a green line, the yellow line, and the red line. But a fun fact, because of the way that the pitot tube is positioned and how we launch our gliders in the program, which is usually on the runway, most into wind, with enough airflow going into the pitot tube, the needle on the airspeed indicator will actually twitch a little bit or make it look like there's an actual airspeed reading. So that's something you might notice if you're on course this summer. But the aircraft is not flying, but the needle is starting to register that there's some kind of airflow happening inside of the pitot tube. So the way that an airspeed indicator is constructed is that it's made up of an anorak capsule, which measures the pitot pressure. The anorak capsule is going to be the same for the VSI and the altimeter. It's just what the type of pressure that it's reading is what's different. And essentially what it is that it's a thin, flexible metal box that once it reaches the pressure in a certain capacity will cause it to either expand or contract. The interior of the case is sealed where the static pressure is measured, and the changes in the pitot pressure cause the aneroid to expand and contract, which then causes the hands on the airspeed indicator to move, and according to what the measurement is getting. So what some of these markings on the airspeed indicator, what do they mean? So these are standard colors used so the pilot can understand what the airspeed indicator is telling you. So on our gliders, the green line or your VSL is your normal operating range. So this is typically the speed that you will fly at all the time. In our gliders, our best L over D is 50 miles per hour. So that's what we're aiming for on every flight when we're not on our final approach or on tow. The white arc, which is not present for our gliders, but will be for a 172, is your range for operating your flaps. So the the maximum speed you can have your flaps extended to. The yellow arc, your VNO. So this is your caution range, the operating range at which only smooth air is allowed to operate. So um, sometimes on final approach, if it's really windy, we'll be flying 65, 70, 75, depending on what the winds are doing. So we would be in our um, yellow line range. The big thing here is you don't want to be flying through turbulent air in those speeds, and as well as you don't want to be doing any abrupt maneuvers either. And then the red line or your VNE, which is your never exceed, because this could potentially damage the aircraft, is that red line. So for our gliders, that green line goes from about 34 to 36 miles an hour to about 65. Again, it depends on the weight configuration of the airplane. The yellow line will go from 65 to 98 or 100, again, depending on the config. And the red line will be either at 98 or 100 miles an hour. Why we have 120, 140, 160 on the VSI, or sorry, the ASI, I'm not sure. But it's there anyway, so we definitely don't fly at those speeds. So now we're going to talk about some airspeed indicator errors. So because it's a mechanically made device, it's prone to some errors. So the first one we'll talk about is the position error. So this means that the eddies that form as it passes over the wings are responsible for causing these errors. And it's when the air around the aircraft differs from the indicated airspeed. It'll no longer correspond to the true airspeed and no longer reflect the aircraft's performance. And for density error, so the atmospheric density varies and changes with the accuracy of the airspeed indicator as well, especially as you increase your altitude, as air density decreases with altitude, but also as temperature increases. So for the density error, so let's say you go to a higher altitude, there's going to be less air particles, so there's going to be lower pressure. So it's going to read a little slower than what's currently on the VSI or the ASI. My apologies. Some other errors, so lag, pretty straightforward. It's slow, right? Again, it's just the working parts of the airspeed indicator can't keep up. Icing, so it's going to give you what's going to happen is that ice is going to block the pitot source in some way. So it's going to give you it's going to give you an inaccurate reading. Like I was mentioning earlier, some aircraft are fitted with pitot heat, so that would be a good way to minimize the chances of icing. But fun fact with that is that pitot heat system is very, very hot. And if you leave it on for longer than anticipated, you could melt your pitot tube. So just be mindful of that when you're flying aircraft with pitot heat. And moisture or water essentially is blocking the tubes, and the water is going to cause erratic airspeed indicator readings. So you won't really know what's happening. Okay, so some definitions here that are important to know. Indicated airspeed is what the airspeed indicator is showing you. So if your airspeed indicator in the glider is showing you 50 miles an hour, you're flying 50 miles an hour. That's your indicated airspeed. Calibrated airspeed is basically corrected for any mechanical errors that could occur. So the calibrated airspeed is your indicated airspeed corrected for instrument and installation error. Some other ones, your equivalent airspeed is calibrated airspeed corrected for the compressibility factor. It's important to note, though, for the equivalent airspeed, it's usually more important for pilots of high-speed aircraft. Not too important for us that fly less than 250 knots and below 10,000 feet. True altitude, or sorry, true airspeed, my apologies, is calibrated or equivalent airspeed corrected for temperature and density errors. So what this reading is going to be the actual speed of the aircraft as it moves through the air mass. So when you're converting indicated to true airspeed, the airspeed indicators are calibrated so that the indicated corresponds to the true airspeed. When you are in a standard atmosphere at 15 degrees Celsius and 29.92 inches of mercury, and it was at sea level. Obviously, that's not going to be the case all the time. So a cool tool you'll have, not so much for the GPTC, but for PPTC. And I'm not really going to elaborate more to this than what I'll tell you here. But you can calculate your true airspeed from using your E6B flight computer while on PPTC. Your instructors are basically will show you how to do that. And all you need to do to find those is know your outside air temperature, the pressure altitude, and your indicated airspeed. This will not be tested, just so you know, but it is good knowledge to have beforehand going on PPTC. So how to remember what's corrected for what? Well, there's a mnemonic that's called iced tea is a pretty cool drink. So to know how to get from indicated to calibrated airspeed, well, you need to correct for your position error. How to get from calibrated to equivalent, you need to correct for your compressibility factor. And equivalent to true airspeed, you need to correct for the density altitude there. So iced tea is a pretty cool drink. If they ask you on an exam, how do you get calibrated from indicated? The answer would be as simple as you correct it for position, right? So there's not much more to that. Okay. Now we'll talk about the altimeter. Any questions so far? Hopefully things are making sense. So as you can see here in the bottom left, you see a picture of the altimeter in the 233. We're going to talk about the construction of it briefly here. So just like the airspeed indicator, it's made of an annular capsule that's set to standard sea level. And as altitude changes, or as the atmospheric pressure changes, the capsule will expand and contract. So it's going to read above sea level. So the moving gears register the change, and then the hands on the altimeter will move accordingly. So normally what we do is if we have an altimeter setting from an airport, we can set it to the altimeter setting, and it'll give us the correct reading. Again, set to what it would be for sea level. So if we're in Villeneuve, for example, like I said, we're 2,250 feet above sea level there. The altimeter setting will be set that kind of reads our zero, even though it's indicating 200 or 2,250 feet. And then as we go up in altitude, the hands on the altimeter move accordingly, and then we just do some mental math to do the conversion from above sea level to above ground level and reading it that way. So the altimeter measures the pressure of the atmosphere, which is the weight of the air above, so directly above where you are. And this weight of the air changes as the aircraft climbs or descends, which causes the altimeter to register that change. Sometimes even when you're on the ground, let's say you leave the gliders overnight and a pressure system moves through the area. So let's say a storm moves in, the altimeter will also register that change in pressure and will give you a different reading than what it was last set to. when you were flying the day before, which is kind of cool, which is why we check it during our pre-takeoff checks and our daily inspections. So the markings on the altimeter, so they go 0 to 9, which indicates 0 to 100, 0 to 200, 300, 400, 500, etc. But then they also indicate hundreds of feet, thousands of feet, and 10,000s of feet. So the outer scale is what represents the height. And the subscale on the inside in between the 2 and the 3 is what indicates the altimeter setting in inches of mercury. That can be corrected or set differently by rotating the knob on the left there. And that's going to cause the needles on the altimeter to change as well. So just like the airspeed indicator, the altimeter is also prone to some errors. So pressure error is the altimeter set to a height an indicated height above sea level at the point of departure and may not be correct after flying some distance. But this error can actually be fixed if the pilot alters the barometric scale or the inches of mercury there to the nearest station's altimeter setting. So while you're flying en route, you actually want to adjust your altimeter as you go so you get the more correct altimeter reading. If you fly from an area of low pressure, or sorry, from a high, so excuse me, an area of high pressure to an area of low pressure, you're going to be flying lower than what's actually indicated. So the mnemonic for that is from high to low, look out below. So the altimeter is reading higher than you actually are. And then on the contrary, from low to high, clear blue sky. So it's going to read, it's going to indicate higher than you are, and the altimeter is going to read lower. Temperature error. So due to the altimeter is calibrated to the true altitude in the standard atmosphere, so you can always assume that the there's going to be an error as a result to temperature. So that's just because it's measured to that standard 15 degrees Celsius. So if the air temperature is colder than the standard air, the true altitude of the aircraft will be lower than what's indicated. So colder air, higher pressure, you're going to get a lower reading. And if the air is warmer, your altitude will be higher. So potentially warmer air, lower pressure, higher reading. The mountain effect. So the winds deflect around large peaks and valleys, which tend to increase the wind speed, which could decrease pressure, which will cause the altimeter to give you a reading that is too high. So the altimeter would decrease and would give you an altitude reading that is too high. And then lastly, mechanical error. So like any other instrument that's made because it's man-made, there will be some lag due to the mechanical instrument itself. Normally it'll catch up as the aircraft levels off from a climb or descent. And sometimes you just have to tap very gently beside the glass of the altimeter and the needles will move and it'll correct itself. I've had to do that a few times myself. Okay. Any questions about altimeter errors? Got a few more instruments to go through and then some review for this class. So next is the vertical speed indicator, or the VSI. So the operations of a VSI. So basically what it does is it indicates a rate of climb or descent measured in feet per minute. And the way that it works with the aneroid capsule expanding and contracting, causing the dial to move, is it's measuring the change in pressure between the capsule and the instrument. So the pressure will usually equalize with the help of a small hole somewhere in the system when it's given read. So for our gliding operations, how we know our climb is normal when we're on tow is our average rate of climb is 400 feet per minute up when we're with the tow plane. And without the tow plane, to know that we're in relatively ideal conditions, the 233's average rate of descent is negative 200 feet per minute. So what that means is if all things go well, you'll lose about 200 feet for every minute if you're as long as you're flying straight and level. The VSI is also prone to errors. So one of the big ones is lag due to the mechanical linkages in the instrument, and it's usually more accurate about 6 to 9 seconds after that reading has been posted. It's this instrument is actually very important for us as pilots for our flight management and our decision making, especially in the glider since we don't have an engine. So it's kind of one of the instruments that we rely on the most, along with the altimeter. Um, so it's definitely the one that you want to pay a little bit more attention to. And next up is the variometer. So our gliders do not have variometer. High performance gliders do. And essentially what the variometer is it's a sensitive VSI. So it's a sensitive rate of climb instrument which takes into account the total energy. It's a lot more accurate than the VSI due to the speed changes. And it measures the sum of the potential energy and its kinetic energy. And the lag is much less. So it's about 1 to 2 seconds. So it's very accurate. And if anybody's flown a glider in a simulator and you hear that like beeping noise, that's a variometer. So they do exist. They are very annoying, but they do help. And you can turn them off if that was something you wanted to do. So if you ever go civvy soaring after you get your license and you convert your from air cadet gliding program to civilian soaring, those gliders will typically have a VSI, like the DG1000s would have a VSI. But yeah, not something you would have to worry about on course. But for your TC exam, you still need to know what a variometer is. Okay, so we'll get into some confirmation questions here. If you want to either put it in the chat or come off of mute. What is the difference between pitot and static pressure? So yeah, what is the difference between pitot and static pressure? Anyone can bite or so yeah, so the pitot is uh, yeah, so sorry, the pitot tube measures the dynamic pressure of the ram air, whereas the static port measures the static pressure in the air. What are the 5 errors that affect the airspeed indicator? And yep, position error is one of them. Good. Density is another one. Good. Ice, yep. Not quite mountain air. Um, yeah, water position. You're right. Water moisture is the one what you'd be looking for, but that's still correct. What are the 4 errors that could affect the altimeter? Temperature is one of them. Good. Mountain air. Yeah, so this is where the mountain air could affect an instrument. Pressure for sure, good. And one last one. Mechanical, good. Okay. Oops. And what occurs when the static source is blocked? I'll give you a hint. There was an acronym that I gave you at the start. Yeah, suck bud, good. Cool. Okay, so that is some of the basic instruments. Okay, how are you get started with the next lecture here, 406.02? We're going to talk about the compass. So we'll talk about the Earth's magnetism. We'll talk a little bit about variation and deviation. We'll talk about the magnetic compass itself, some errors, how to read the compass, and compass swing. We've got two more. We've got this lecture, one more after it, and then that'll be everything for this evening. Okay, so we'll start talking about Earth's magnetism. So as we all know, the Earth acts like a magnet with a north pole and a south magnetic pole. And basically what's happening is inside of the Earth, there's currents of molten iron flowing around. And what's happening is that it's causing positive and negative charges to be generated at the poles, creating an electric magnetic field. The compass needle is influenced by the Earth's magnetic field, which is going to lie parallel to one of the magnetic lines within its north-seeking pole pointing to the magnetic north. There's a difference between the magnetic north and the true north. So the true north or geographic north is the North Pole. The magnetic north actually moves over time. So that's why we have things like compass swing and compass correction cards and things like that. So that's important to know, is that the magnetic north does move. As you can see on the graph there, started quite, I think that's in the 1800s or something by the looks of it, where it started quite basically right in Canada. And now it's moved its way up relatively towards the geographic North Pole. So variation. So the true north and south poles correspond to the Earth's axis of rotation. So like I said, they're the geographic north and south pole. The magnetic poles do not. So the North Pole is not a stationary point, but moves in an erratic circle. But the big takeaway from this here is, what is variation? So variation is the angle between the true north and the magnetic north. So that's a very common exam question, especially when you talk a little bit more about navigation. What's the definition of variation? It's the angle between the true north and the magnetic north. And variation does change year to year because of the Earth's wobble on its axis. So, for example, the variation over Edmonton is about 14 degrees to the east. And it does change as you go further west, and it does change as you go further east. So a good way to know what the variation is by looking on a current VNC chart, which I think you'll talk about next week in navigation a little bit further in depth. Deviation. So this is the angle which the compass needle is deflected from the magnetic north. So this is a result of the magnetic fields from metal and electronics in the aircraft. Yeah, usually the deviation is small, somewhere in between 2 to 5 degrees, but it's corrected with a compass swing, which we'll talk a little bit more about at the end of the presentation. So again, variation and deviation, those are from experience and from what I can remember when I was a cadet, very common exam questions. So the magnetic compass. So how is it built? Well, there's two north-seeking magnets that are attached to a float and a compass card. The compass card is not currently pictured in this photo, but they do exist. And it's mounted on a pivot so that it's free to rotate. That's a big important thing for the compass. The whole assembly itself is mounted in a compass bowl, which is then filled with alcohol. This liquid actually helps reduce the weights and the magnets, help the magnets flow more freely. The lubber line is marked along, is a mark aligned with the longitudinal axis of the aircraft. So if you look at the compass and the glider here, there's that white line that goes straight up and down inside the compass. That's the lubber line. And then the pilot will read the aircraft's magnetic heading based on what's directly behind the lubber line. Very hard to read in a turn because the compass is moving. So always make sure that if you want to get the most accurate compass heading, that you're flying in straight and level flight. And trying not to accelerate or decelerate as well, because that also can cause some magnetic compass errors, which we will talk about shortly. So some compass errors. We're going to talk about the northern turning error, and then the acceleration deceleration error and magnetic dip. So the northern turning error. Long story short, the compass always wants to point to the north. So this is only really occurs on turns to or from the north. So it's more noticeable the closer you are to the poles, and it decreases as you get closer to the equator. So on turns from the north, so you're currently turning away from the north, the compass is going to lag, and that's because the magnetic connection there wants to stay facing north, so it's going to lag. On turns from the south, so you're turning from the south towards the north a little bit, the compass is going to lead, so it's going to get ahead of what it's actually going to be reading. So you just got to give it a sec to actually read what the aircraft is facing once you're back at straight and level flight. So hopefully that makes sense for the northerly turning error. So again, also a very common exam question. On turns from the north, compass will lag. Turns from the south or to the north, compass will lead. Next is the acceleration deceleration errors. So a big thing to note with this is that this is only on east or west headings. So when the aircraft increases its speed, there's a force that's going to set up in the direction of its moving. And that acceleration is going to act through the pivot point on the compass. And then the magnetic force on the compass causes it to dip when it accelerates. So there's another mnemonic for this. It's called ANS. So accelerate north and decelerate south. So hopefully that one makes sense too. That one's relatively simple. Also an exam question that I have seen in the past. So the magnetic dip error. So what's happening here is that the Earth lines of force are horizontal at the equator, but become more vertical near the poles. So this is actually going to cause the compass to dip at higher latitudes. So the more closer you go towards the North Pole, the compass is actually going to dip. So in order to compensate from this happening, sometimes they put magnets in the compass to balance it while it's on that pivot. So that the center of gravity is displaced further backwards, preventing it to dip even further because of that vertical force as you get closer to the North Pole. So could be more common to see here in Canada, especially as you fly closer towards the Arctic Circle, but not too terribly noticeable if you're flying in the prairies or in Ontario, places like that. So how to read the compass. So like I mentioned earlier, the lubber line indicates the direction that the aircraft is currently moving in. And the most accurate level, or sorry, the most accurate reading is going to be when the aircraft flies at a constant speed and heading at a level attitude. Um, so attitude means it's kind of like how's the nose pointing? Is it a nose up attitude, a nose down attitude, or is it a wings level attitude? So you're flying straight and level. Hopefully that makes sense. Pretty straightforward, right? Like I mentioned earlier, don't read it in a turn. So like I said, when reading it, not in a turn or a banked attitude, not when you're accelerating or decelerating. Um, and if you're flying in turbulent air, just try and take an average reading of what it's saying. Um, and then while you're on the ground, do it while you're either stopped or if you're taxiing in a constant speed. Uh, Especially if you're taxiing and you're about to turn, as you turn, the compass is also going to turn as well. So just be mindful of that. Um, yeah. And importantly, too, while you're on the ground, you definitely want to make sure that the compass is free and floating, because if it's not, then you know something's wrong and the compass actually isn't going to work. And it is a legal requirement for the compass to be functioning for the aircraft to fly. So, compass swing. So, the compass swing is done for correction for deviations. Remember, this is caused by other magnetism or electrics in the aircraft, like the radios, for an example. So what happens is they'll actually bring the aircraft to a compass rose that's painted on the ground, and it's going to give accurate readings of where your magnetic north is and east and west and things like that. And then the aircraft is lined up on the rose with the radio on and the engine running just to get all the electrical items on. So it will give you the reading. And then when you are, so basically what's going to happen is they're going to, let's say, move the aircraft from 000, so directly north to 030 on the compass card, or sorry, on the compass rose on the ground. And then what's going to happen is they're going to see what the compass is reading and how it differs from the compass rose on the ground. And then what you see there is what they're going to put in the compass card. So like you see on I don't know if your photo's blurry, but my photo's blurry. So if you guys can't see that compass correction card, let me know. Um, but it'll say like 2 or 4, and then the heading, so like 030. And then underneath it, it's going to say steer, and then it'll say something like 031 or 029. So you want to steer that um, direction on your compass to actually get the correct magnetic heading, if that makes sense. So it'll offset a little bit, but to fly the proper magnetic heading, you might have to fly a little bit differently for um that. Okay, let me see if I can let's go through the confirmation cards here or questions here, and then I'll find you guys a better photo of a compass correction card. So what is the northern turning error? Northerly turning error. Yeah, good. So when you're turning to the north, it's going to lead, and when you're turning from the north, it's going to lag. Good. Um, Next question. What is the acceleration and deceleration error? Yeah, so when you accelerate, when you accelerate, you're going to get a little dip to the north, and when you decelerate, you're going to get a little dip to the south. Um, and on what type of heading would you have this error? Yeah, east-west heading's good. Okay, what is deviation? Yeah, so it's the angle that the compass needle is deflected from the magnetic north caused by magnetic fields and other metal and electronics in the aircraft. Good. And then the next question, what is variation? Yeah, so the variation is the angle between your magnetic north and your true north. Good. Cool. Seems like that made sense. Hopefully, that made sense to everybody. Are there any questions from this class about the compass in particular? All right. So for tonight's last class or last lesson of the night, we're going to talk about introduction to decision making, which I know you might seem or might wonder why is this in ground school? Well, it's part of human factors and pilot decision making, but also in the gliding program in particular, this is a big part of human performance in military aviation. So, as a pilot, decision making is critical in all phases of flight. It's important before you go flying, during your flight, and even after you go flying. So it's important to have good situational awareness built regarding what's happening, or what's happened, what is happening, and what's going to happen later on. And all of these factors influence your decision-making process. So we're going to talk about it a little bit this evening. I'm not sure what the expectation is regarding this on the exam. Again, if it is on the exam, it'll be brought up in some capacity during the review periods in a week and a half's time, almost 2 weeks. And yeah, but for now, let's talk about some decision making. Okay, so we definitely want to provide a systematic approach to decision making that can be used to explain the process and the elements of decision making. We want to analyze decisions and troubleshoot the errors, and we also want to assist ourselves in making more effective decisions in the future. Um, yeah, so another advantage of using a system that is like this is to reduce errors, speed up the process, and um, make a more user-friendly process that can be standardized. So we'll talk about decision-making process, three critical resources, controlling the decision-making process, and when things don't go right. So the decision-making process itself, as you can see here, there's seven important factors regarding the process itself. So we've got the task and workload management, communication, threat and error management, SOPs, situational awareness, team performance, and individual factors. On the gliding course, these are some of the things that we are actually looking for while you are flying. So regarding the process, it's really important to have a good general idea of what's happening all around you. So for an example here, the example that I have for you is that let's say we're in the glider and we're at 2,400 feet above the ground and we want to practice incipient spins. So what are some of the things that we need to take into account before we conduct one? Well, we need to go through our SOPs, our standard operating procedures. Um, in this case, do we have enough altitude as per the Air Cadet Gliding Program Manual or the 242? And the answer is no. We need at least minimum to be recovered. Well, it's possible. You need to be recovered by 2,000 feet above ground level. So it's possible that you could do it. Another SOP or standard operating procedure that we need to do is that we need to conduct a safety check to make sure that the aircraft is safe and the pilots are safe to conduct an abnormal flight maneuver. Situational awareness. Are there other aircraft in the area, other hazards? Some threats. Is the location of the other airplanes, are they below us, right? Are they above us, behind us, beside us? Other threats could be clouds in the practice area. Are we going to spin into a cloud, right? Things and lose perception of the ground. Those are the kind of things that we factor in to the decision making process. So basically, you want to have good knowledge of what you're going to do and the things regarding it, and then pay attention to certain things. So when it comes to setting goals, goals are really just a reference point in the decision-making process. So it's really important that we're able to kind of navigate what we really need to do to get us to succeed in making these goals or the decisions that are being made. So this leads us to talking about the APA model, and we're going to talk about it a little bit more later on in the lesson. So APA is for awareness, implications, plan, and actions. Right. So we get an idea, we put the goals into our head, and then we need to respond in some capacity for those goals to happen. So the three critical decision-making resources we have is going to be knowledge, attention, and time. So I just wrote down on my notes here, but so in terms of knowledge, it's really important that we know what's happening around us, right? That, like we had discussed in the previous slide, just kind of knowing what do we know about the process, what do we know that could happen, what is all going around. Previous knowledge and previous experience is also very helpful in this situation as well. When it comes to attention, we need to pay attention to some of the major factors. We can't just pick, three things over here and two other minor things. We really need to be able to switch our focus to the maneuver or the events that are about to take place. And then time, right? Sometimes there's no immediate action that's required, or sometimes it needs to be prompt, right? So there are some downsides to having a lot of knowledge and experience in aviation. It can cause complacency and inattention, right? So you get really comfortable with doing a certain maneuver, a certain standard practice, that you just stop paying attention to some other factors. And I'll get into an example here momentarily. Everybody perceives the world a little bit different, so some decisions that made in the future, we often draw on past experiences. And it might not be the same every time. So it's easy to think a current problem can be solved in the exact same way as it was in the past, without actually taking into account some differences that may seem minor, but in fact are critical. So an example that I have for you here is knowledge. So we know we're close to the boundary in one of our practice areas, and we need to turn to stay inside of that practice area. Tow aircraft are outside of the practice area and present a hazard. So we are not to fly outside of that practice area as per the flying orders or the rules. So that would be the knowledge that we have, right? Attention. So we need to switch our focus from, let's say, we were just practicing forward slips, but we need to actually focus our attention away from that and to change our focus to turning away from that boundary, right? So we begin to scan to update our sight picture of what we see in front of us to ensure that we're flying into an area that is clear of traffic and avoid complacency, right? And in this scenario, no immediate action is required, but we should probably be getting on it pretty soon, right? We need those turns to be prompt. So when we talk about knowledge a little bit more in depth here, so there's three big things with knowledge. There's experience, perception, and goals. And these combined create your mental model that is understanding of how things work. So, a person may enter a situation with their existing knowledge. However, in order to react to a situation or an event, um, you as the individual need to give adequate attention to the task or the issue or the goal that you're trying to accomplish. Um, and then the amount of time available is actually going to determine the amount of attention that can be allocated to the um, um, the decision-making process. Sorry. So sometimes high levels of knowledge will help to save time and allow us to focus on our attention on other situations as required. Hopefully that makes sense. And we can develop and improve all of the above as we gain more experience in flying. The next critical resource is attention. So capacity for attention is limited to and susceptible to overload. So attention resources are essentially serial in nature and we as humans aren't actually very good at multitasking. You may think you're good at multitasking, but biology speaks otherwise. So sometimes we can only attend to one conscious task at a time, even though the various tasking goals we can be managed need to be juggled by moving from one to another, attempting to give each situation adequate attention, and then you need to decide what's most important. So an example for this would be a glider enters the downwind leg of the circuit, right? So the pilot has to use their attention resource to attend to drift from the upper winds, runway position, any lift and sink, completing their pre-landing checks, and analyzing for any other traffic in the area. So an inexperienced pilot might have a lot of difficulty when they get to this section because they're going to be task saturated, which means like their bucket is full. They've got so much to do and can't effectively cycle all of their attention to complete all the tasks, right? Whereas a more experienced pilot might have more time to effectively manage where he needs to put his or her attention on the things that are getting completed. So hopefully that makes sense. I know that's kind of a big verbal vomit there. And lastly, our other critical resource is time, right? So our information processing capacity and the amount of time available is usually what creates a bottleneck in decision making. So, if we had all of the time in the world, we could maximize our prerequisite knowledge to maximize our situational knowledge and correct for any decision making errors. But frequently, we have to make decisions that are compressed for time, especially while you're flying, because the situation is changing all the time. And if you were flying 20 minutes ago, your flight 20 minutes ago may not be the same as it is in the next 20 minutes, right? So if time is determining how much information we can process, then we can either increase our knowledge or focus our attention on other aspects of what we are trying to do. So looking at the graph here, let's say if you have higher accuracy, you're going to spend a lot more time trying to get there. Where if you're less accurate, you'll be less accurate if you speed up. So before and while you go flying, you definitely want to make a plan based on what's most important with the knowledge that you have, where you're paying attention to, and how much time do you really have. And that's kind of what takes us to our APA model again. So awareness, what's our starting goal and what do we already know? Implications, what is the current goal? Have we added any knowledge? Plan, what's the difference between our awareness and our implications, which sometimes these differences allow us to make a new plan or goal. And then act is to select your new actions to achieve your goal. That's where the APA model helps in controlling the decision-making process. So awareness a little bit more in depth. So maximizing awareness as to what's happening in the surrounding environment and how we are currently positioned in relation to your higher level goals. So these are some of the questions you can ask yourself in order to be aware, right? So what are we trying to accomplish? Um, what's working? What's not working? What are the priorities? Things like that. How has the situation changed? Um, you know, oops, in this case, bliss is not, or sorry, ignorance is not bliss. What you don't know can in fact hurt you in aviation. So it's really important to be aware of what's going on. So once we ask ourselves these questions, well, then what's our next step? Well, then we get into implications a little bit more. So then we can ask ourselves the following questions. So what does it mean? How is it going to affect us? Is this an acceptable level of risk, right? And we work through the implications of these events. And the more accurate our perceptions are and our existing skills and knowledge, then the more accurate we could understand the implications of what's going to happen. When we plan our actions, right? Uh, what are the goals and the priorities for this? What options or backups do we have? How can we best allocate our resources? Um, right. So you want to plan based on the most amount of information that you have. Revise the plan as the situation changes. Develop a contingency plan with to cope with a variety of critical events as well. And then once you have all of that additional information, then you move into the act of the decision-making process. So you would execute the plan. Um, so how do we control this process? Well, we reinitiate, sorry, the APA model process. So you definitely want to be responding to changes and errors as they go. So for example, like if you're flying the glider in the circuit and you have a lot of lift, well, you want to open your spoilers to spoil the lift and increase your rate of descent a little bit more. But then if you come across a big chunk of sink in the air, well, then you need to close your spoilers and adapt your circuit pattern to be a little bit differently depending on the conditions. So that's how we reinitiate that APA model. So we're constantly thinking of the awareness, the implications of what's going on, plan our next step, and then act upon it. So the APA model gives us three critical resources. It gives us a systematic approach to making effective decisions. Um, and in reality, what's important here is that to know we must attend, and to attend we must have time. So the three critical stages, or sorry, three critical resources interact with each stage of the decision-making process. So, do you think it's acceptable to proceed straight from awareness to give, or sorry, straight to action? I'll let you guys either put something in the chat or come off of mute if you'd like. Is it ever acceptable to proceed straight from awareness to action? And if you think so, could you give some examples? So if you need some help, I can give you an example here. So it is possible, but you need to be really careful and wary of the circumstances because in our case, for example, emergency procedures, so there's implication and planning has already been considered in advance, especially because we practice for um, glider rope breaks, for example. So you need to be really mindful of time and critical events. So again, they have knowledge, time, and attention. Um, so which of the following do you think Or which of the following factors do you think influence decision making? So do you think the pilot's state of fatigue is going to influence decision making? And if so, why? Yeah, so definitely all of the above will influence decision making, but let's kind of just briefly go over each one of them. There's no right or wrong answer. It's kind of an open discussion. I just want to see what your thought processes are. But pilot state of fatigue, um, got an answer here. Vary because fatigue can result in not well planned acts. Yeah, absolutely. If you are fatigued, you won't be thinking straight. You're definitely not thinking as fast, so therefore your reaction time is going to slow down, right? Um, Yep, state of fatigue will definitely impact your awareness, right? Sometimes you'll see people drinking coffee, flying for or before they go flying. Um, Coffee doesn't actually reduce your fatigue. I don't even think it really helps you be more alert. So just really be mindful of your fatigue levels when you go flying. Do you think published operating rules also influence decision making? Yeah, fatigue will affect your decision making if you're not sleeping well. Absolutely. In terms of published operating rules, right, you need to know basically what you can or can't do in certain situations, right? Exactly, right. The operating rules limit what the pilot can do without risking too much or creating a danger. Absolutely. Knowing the rules can help in decision making. Absolutely. Those are very good answers. What are the three essential resources for decision making? You can go ahead and just type them in the chat. Yep, knowledge is one of them. Knowledge, attention, and time. Very good. And in what kind of situation does it become necessary to speed up decisions and implications at the risk of increasing the risk of errors? So in this case, when time is very limited, such as emergency situations. Yeah, very good. Okay, true or false? The capacity to process information is limited in the same way for everyone. Yeah, very good. False. Everybody is going to be different, right? Everybody perceives things differently. Everyone has different experiences. So those are things to keep in mind. The way we approach a task can change our ability to process information. True or false? The answer is going to be true, right? It really depends on how we're able to, um, process the information, whether we're motivated or not to do so. The number of hours of sleep can influence a decision. True or false? Yeah, definitely true, right? Lack of sleep limits your ability to process information. That's not even just for flying, that's for everyday life, right? Especially in school, if you're not sleeping well, if you're tired, you'll have a tougher time with the material that's being taught. And decision making, true or false, decision making using the APA model ends as soon as a plan is completed. So the APA model is that awareness, implications, plan, and act. Yeah, very good. False, because it needs to be, it's important to continue the loop in order to modify the plan if necessary. Good. Okay. Are there any questions? I know that was a lot. That was a lot of verbal vomit, but are there any questions regarding decision making?